Greetings again from our nation's capital. It's Monday morning. The baby's asleep. The toddler is at school. And we're going to talk about inner products. So, you remember when we first started talking about vector spaces. You've been familiar with vector spaces forever. That is, vector spaces like R2, R3, and then, yeah, we can generalize. We imagine R4, R5, R6, R42, just as vector spaces in the sense that the vectors are columns of n numbers, right? So we have an idea of what the vectors look like, and we have all kinds of operations that the vectors obey. Okay, and then we generalize vector spaces. We said, what if we have other objects that have the same properties? Then we can call them vector spaces. And we found vector spaces that consist of polynomials or functions or matrices. So now we're going to look at inner products, which are a generalization of the dot product on the good old vector spaces R2, R3, and so forth. So we want to generalize dot product so that we can apply it to vector spaces with polynomials or matrices or functions or anything, as long as it's a vector space. So what we're going to do is we're going to define what an inner product is. An inner product is a function. It's a function that associates a real number to each pair of vectors in a vector space V. Now we're sticking with real numbers. We could have complex numbers, we could have complex vector spaces, but we're not going there right now. So inner product is a function that associates a real number to each pair of vectors in a vector space V. It's a generalization of the dot product, because remember, in the dot product you take two vectors, you multiply each of the components and add them up, and you get a real number. So the dot product in R2, R3, or Rn is an inner product for those vector spaces, because they take two vectors and they associate a real number. But we want the inner product to have certain properties. The first property is usually called the symmetric property. When u, v are vectors in a vector space V, this symbol is typical for the inner product. The inner product of u and v is the same as the inner product of v and u. That's the symmetric property. We also want these two properties are typically together called the bilinear property. If we take the inner product of u plus v with w, that's the same as the inner product of u with w plus v with w. If we take the inner product of a scalar c, a real number scalar c times vector u, take that and do the inner product with v, it's the same as doing the inner product with u and v and then multiplying by c. The last property is if we take the inner product of a vector with itself, then that's going to be greater than or equal to 0, and it's going to be 0 if and only if the vector is actually 0. So if you think back to dot products, say in R2, so if you have two vectors, u1, u2, v1, v2, so those are the components of the two vectors u and v. You multiply u1 times v1 plus v1 times u1 times v1 plus u2 times v2, and you add them. That's our dot product. That's an inner product on R2. Notice the symmetric property holds because it doesn't matter which order you multiply them in. These two properties hold. If you do a little algebra with it, you can see that these two properties hold and this one holds for the dot product. So these are the key properties that mathematicians have decided to abstract to inner products from dot products. Also, we can define certain things like the norm of a vector is the square root of the inner product of v with itself. This is a generalization of length. Now, is this length when v is a polynomial or v is a function or v is a matrix? This is a generalization of the idea of length from R2 or R3. We also say that two vectors are orthogonal if their inner product is 0. Again, do we have a picture we can draw? Maybe not. But we can abstract the idea of orthogonality. Okay, let me go to the next slide. Let's look at some examples. We already mentioned that the regular dot product is an inner product. But we can also, let's say we're in the vector space R2, we can also define a weighted inner product. So we actually have a different coefficient multiplying this first, the product of the first two components and the product of the second two components. We have different coefficients. That's called a weighted dot product. It is also an inner product. How do we know? Well, we'd have to check each one of these properties. And it's really just a matter of applying the algebra and checking it. And I'm pretty sure Ley does this in his first example. Okay, let's go on to some more interesting examples. What about polynomials? So I'm going to let u and v be vectors in this space. This space is the set of all polynomials of degree less than or equal to 2. That's what the script P2 is. All polynomials less than or equal to, of degree less than or equal to 2. So I'm going to write out u. U is some constant plus u1 x plus u2 x squared. V is the other polynomial that I'll write this way. Now I could have used a t instead of an x. I could have used some other variables, but doesn't matter. Doesn't matter. We can define an inner product. It's hard to get out of saying dot product. An inner product of these two polynomials we could define as just the sum of the products of the coefficients in the polynomial. That is a dot product. And I'm going to give you that as an exercise to check that that's a dot product. But it's not the typical dot product that textbooks usually refer to. Your Ley book refers to this dot product. There's another way of defining, dot product. There's another way of defining an inner product on this space, P2. This is an inner product. Given n distinct real numbers, distinct meaning different. So we have t sub 0, t sub 1 through t sub n. So let's say u and v are in P2. So we're going to say the dot product is the product of, is the sum of the products of the polynomials evaluated at each of these distinct real numbers. So it's going to be u of t sub 0 times v of t sub 0 plus u of t sub 1 times v of t sub 1 plus dot 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 u of t sub n times v of t sub n. For instance, this is an example from, this is number 4 in the exercises in the Ley book. So he uses P's and Q's. Okay, we'll use P's and Q's instead of U's and V's. He uses T's. Fine. So we say one polynomial is 3t minus t squared. That's obviously in P2. It's a polynomial of degree less than or equal to 2. Q of t is 3 plus 2t squared. Okay, and our distinct real numbers are -1, 0, and 1. So what do? We evaluate the polynomials at these three places. So p at -1 is going to be -4. Q at -1 is going to be 5. Multiply. P of 0 is 0. Q of 0 is 3. P of 1 is 2. Q of 1 is 5. We multiply and add and we get -10. Now usually when I get to an example like this, somebody says, wait a minute, the dot product is supposed to be, the inner product is supposed to be positive. No, the inner product can be negative. It just has to be a real number. What has to be positive is if you take the inner product of a vector with itself. Then that has to be positive. Okay, so this is an example of an inner product defined on a polynomial space. Okay, let's try another example. An inner product defined on a function space. This time we have the vector space of all continuous functions f and g on a closed interval ab, where a and b are real. So we have the inner product of f with g is going to be the integral from a to b of f of t times g of t dt. For example, let's say the space is a set of all continuous functions from 0 to 1. Here's one of them. Here's f. Here's g. F is 5t minus 3. G is t cubed minus 2. So to get the inner product, we take the integral from 0 to 1 of 5t minus 3 times t cubed minus 2. Multiply that out, and we get 5t to the fourth minus 10t minus 3t cubed plus 6. Take the integral, and we get this. Then we evaluate the integral from 0 to 1, and if my arithmetic is correct, and I think it is, it's 1 1/4. So this is a kind of a standard inner product on a function space. Okay, so what have we done? We've defined inner product on a vector space. By the way, a vector space with an inner product defined on it is an inner product space. So we saw how it was a generalization of the dot product, and we saw some examples of how you can define inner products for vector spaces that are polynomials and vector spaces that are functions. And we can even define a weighted inner product, a weighted dot product as an inner product on the regular spaces Rn. So I gave you a problem to do, to send to me. It's on Moodle, and you can send it to me by tomorrow night. And we're going to have one more video on Cauchy-Schwarz inequality, and we're going to look at, okay, we've got a generalization of the dot product. So we can use that to find projections, to find orthogonal vectors, and to use the Gram-Schmidt orthogonalization process to get an orthogonal basis. So we're going to see that in the next video. Bye for now.